Hello everyone, this is Dr. Webb. In this video we're going to be talking about the calculus of logarithms. So logarithms, these are the inverses, the functional inverses of exponential functions, right? And so any equation that you can write using exponential functions, you can invert it using logarithms. So what I mean is if we had something like 3 squared is equal to 9, well, using logarithms, we can invert this to log base 3 of 9 is equal to 2. Right? And so the idea of what a logarithm does, what a logarithm is meant to do, is to pull out this exponent. Okay. So, sort of writing this the same way, this is the same thing as what we said before, is if I have, so what we were saying before is that the last example we had 3 log base 3 of 2 equals 2 equals log base 3 of 3 to the 2. And the part that looks probably most familiar is this 3 to the 2 is 9. And so in the last example, we really were using the right half of this equation. Now, as we saw before when we were talking about derivatives of exponential functions, there's one base that we particularly like, and that's using base e. Right? And so in base e, we give the logarithm in base e a special name. It is the natural log written ln of x. So there are, commonly speaking, there are some logs that appear more often than others. Usually in mathematical terms, we most often use the natural log because of its nice properties, because of its connections to the base e. Some other ones you might see log base 10. This is used quite often in geology, sometimes in chemistry. Log base 2 pops up quite often in having to do with computers and computer science. But for our purposes in this class, anytime that we use a logarithm, it's going to be the natural log. Okay, so the natural log, this ln is just shorthand for log base e of x. And so e to the x and natural log of x, they undo each other. So e to the natural log of x is equal to x, and the natural log of e to the x is equal to x. Okay, so let's think about what the graph of the natural log is. So right now we have the graph of y equals e to the x. And then this red line here is just the line y equals x. And so since the natural log is the inverse of e to the x, its graph is going to be the mirror image over the line y equals x, so over this red line. Right? And so before we do that, let's note some points on the graph for y equals e to the x. So 1, for every exponential function where there's just a 1 out in front, it's always going to go through the point 0, 1. So this is the point 0, 1 is going to be on this graph. And if we plug 1 in there, we're going to get just e. So it also contains the point 1e. So when we flip this over, we're going to get these same points with the x and y coordinates flipped over. So when x equals 1, y is going to be 0. So it's going to contain the point 1, 0. And then when x is equal to e, which remember is about 2.7, so right about there, that's about where it's going to cross the line y equals 1. So it's going to contain the point e1. And so now we can think about flipping this whole thing. And let's make it look nice. And there it goes through. See, it contains the point 1, 0, just as we said, and goes through this point e1. matching that point there and that point there. Okay, and so this is the graph of the natural log. So one thing to note, in e to the x, limit of e to the x as x goes to minus infinity is equal to 0. And so what that corresponds to, so this has, e to the x has a horizontal asymptote at 0. So a horizontal asymptote, when we flip it, becomes a vertical asymptote. And so the flip of this is that the limit as x goes to 0 from the right of ln of x is equal to minus infinity. And so we have these flips here, 0, the value of the limit gets flipped in for the x value, and vice versa down here. Same as we saw in equations using natural log of x versus e to the x. Okay, so let's do an example just using natural logs a little bit. We're not even taking derivatives of natural log yet. We'll do that in a minute. So the question is, the city has 50,000 people and is currently growing at a rate of 1,500 people per year. If the population grows exponentially at the current rate, when will the population be increasing by 2,000 people per year? Okay, so we have an exponential function. So remember that exponential function, we're going to let current time equal t equals 0, or let's say x equals 0. So our function is going to look like we're doing this in base e. So that's our standard exponential function. We have to figure out, first we need to figure out what c and r are. And so we know, actually instead of calling this y, let's call this f of x. And so the information given, the city currently is at 50,000. So we'll say that means that f of 0 equals 50,000. And if we plug 0 in for x over here, c times e to the r times 0. R times 0 is just 0. E to the 0, that's just 1. And so this is saying c is equal to 50,000. Okay. And then we're given that it's currently growing at a rate of 1,500 people per year. So that's telling me something about the derivative. And so we got to take the derivative of this function. We know that c is equal to 50,000. And so, well, let's say we have 50,000. And then we have to take the derivative of e to the rx. So we've done this a couple times before, but let's write it out quickly. So we can think about e to the rx as being, using the chain rule by using the outside function as e to the x, and our inside function is r times x. Derivative of the outside is just e to the x again. Derivative of the inside is just r. So plugging this in, we're going to get the outside, e with the inside plugged in, rx times the derivative of the inside is r. And so the way this is going, our derivative of the outside with the inside plugged in, times derivative of the inside, times the derivative of the inside. And so then the information we're given here is that f prime of 0 is equal to 1,500. And so plugging in 0 for x, that's going to turn that into 1 again. And so we have 50,000 times 1 times r is equal to 1,500. And so then r is equal to 1,500 over 5,000, 50,000. And I believe we can cross out some of these zeros. So we have 15 over 500. which I think simplifies down to 0.03. Right, if we divide 15 over 500 divided by 5, we get 3 over 100. And let me just double check. Yep, 0.03. Okay, so now we know what our function is. So let me delete all of this. Okay. So we have that our function is 50,000 e to the 0.03x. R is 0.03. Okay. We saw that the derivative is c times e to the rx times r. So I can rewrite that as bring the r to the front. So r times c e to the rx. Right? And so r times c, that is 0.03 times 50,000. That's the 1,500 again. So our derivative is 1,500 e to the 0.03x. And then the question is when, for what value of x, is this going to equal 2,000? So let's set that equal to 2,000. Let's do some erasing around here. Okay, then that x should be up there in the exponent. So we're going to use a logarithm, but to use a logarithm, we got to get the e to the 0.03x by itself. So we're going to divide by the 1,500. So we have e to the 0.03x is equal to 2,000 divided by 1,500. And zeros cancel off. 20 over 15. That simplifies down to 4/3. Okay, so now we want to pull out this exponent here. And so we can pull out this exponent by taking the natural log of both sides. And that's going to cancel out the left-hand side. So taking the natural log of both sides, on the right, we'll have natural log of 4/3. On the left-hand side, natural log of e to that is going to cancel. Those two are going to cancel each themselves out. Left with just 0.03 times x. And so then we can divide by 0.03. And plugging this into our calculator, natural log of 4/3 divided by 0.03. I get that this is about 9.59. So a little bit more than 9.5 years. Okay, so the answer here is 9.59 years. Okay, so now let's talk about taking the derivatives of logarithms. And we're going to use a similar trick to what we used before when we were figuring out derivatives of roots, right? So we're going to use that we know the derivative of e to the x, and that e and natural log are inverses of each other, right? So same trick we did before. X is the same thing as e to the natural log of x. That's what it means for e and natural log to be inverses of each other. So then when I take the derivatives of both sides, I know the derivative of x and e to the x, and so I'll be able to figure out what the derivative of natural log has to be. Okay? So on the left-hand side, we're just taking the derivative of x. And just taking the derivative of x, that's going to pop out a 1. Now on the right-hand side, we've got to take the derivative of e to the natural log of x. using the fact that we know e and trying to figure out what natural log is. And so this is going to be similar to how we've done derivatives with e to the x before. We're going to use the chain rule. Our outside function is e to the x. Our inside function is ln of x. Derivative of the outside, derivative of e to the x is just e to the x. And then derivative of the inside is what we're trying to get. It's the derivative of natural log. Okay? And so what the chain rule says this is going to be is you take derivative of the outside, e, with the inside plugged in, ln of x, and then multiply by derivative of the inside. D over dx. That's what we're going to be trying to solve for. Okay, so this is what we get for the derivative of the right-hand side. And let's make that look nice. There it is. And then if you notice, we have this, we got e to the natural log of x again. And what does e to the natural log of x equals? Well, it equals to x. So we can swap that in. And so we end up at the end is 1 is equal to x times whatever the derivative of natural log of x is. Well, we can solve for this. Solve for this just by dividing by x. And so what we end up with is that the derivative of natural log of x has to equal 1 over x. And this should make us really happy. And so if you think back, the way that I think about this is it kind of fills in a gap with the power rule, right? So we talked about derivative of powers. The derivative of x to the n is n x to the n minus 1. And this works for all n. And so if you think about this, you can pretty much get any possible power of x here except for x to the minus 1. Because if you wanted to get x to the minus 1, well, then you'd set n to be 0, but then you'd be multiplying by 0 out here. So it's not possible to end up with x to the minus 1 really by itself on the right-hand side. So where is that gap filled in? Natural log fills that in for us. So natural log of x is what gives us x to the minus 1 as its derivative. And this actually makes natural log of x useful in a whole bunch of other areas. This pops up quite a bit in chemistry because of this fact. If you think about derivative talking about a rate, well, if the rate of something is 1 over x, that means that it's inversely proportional to whatever it is. So if the rate is 1 over x, that means that growth is what we'd say is inversely proportional to whatever x is. And so what function gives it to us? Well, it tells us that the function is related to a logarithm. And so there's lots of things that pop up where something is inversely where its growth is inversely proportional to its size. In any situation there, that's when we end up talking about a logarithm. Okay, so let's do a practice problem taking a derivative using logarithms. So here we're trying to take the derivative of x squared times the natural log of 2x plus 1. So looking at this, I've got x squared times the natural log of 2x plus 1. So this is a product. And if it's a product, then we got to use the product rule. So Using the product rule, my first function is x squared. My second function is ln of 2x plus 1. Derivative of x squared I can do. That's going to be 2x. Now to do the derivative of ln of 2x plus 1, well, we should think about that as being a chain rule problem where the outside function is natural log. On the inside, we're plugging in 2x plus 1. So the derivative of outside, we just saw the derivative of natural log of x is 1 over x. Derivative of the inside here, derivative of 2x plus 1 is going to be 2 coming from the 2x, and then the plus 1 goes to 0. So it's just 2 there. So putting this together to get g prime, I've got my derivative of the outside with the inside plugged in. So 1 over 2x plus 1 times my derivative of the inside, which is 2. And so maybe we rewrite this nicely, like so. And so now we have everything that we need to do the product rule. And so remember, the product rule is f prime g plus f g prime. And so we can write it in here. F prime is 2x times g natural log of 2x plus 1 plus f is x squared times g prime 2 over 2x plus 1. And there's our answer. Okay, so 2x times natural log of 2x plus 1 plus x squared times 2 over 2x plus 1. Okay, so our practice problems that we'll go over Monday morning. So first we got 3 derivatives using natural log. So first take the derivative of natural log with this quadratic, 5x squared plus 3x plus 7 plugged in. Then take the derivative of x cubed times natural log of x quantity squared. So it's not natural log of x squared. It's take the natural log of x and multiply it by itself. And then finally, we have a quotient, 3x plus 2 divided by natural log of x cubed plus x. Okay, and then secondly, sort of similar to the previous problem we did, here's an exponential function, 5 times e to the 0.25x. At what value of x will the derivative equal 10? So I will see you Monday morning. Bye.